Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. Yesterday, we actually did all the work necessary to make a rotating camera, but we didn't have a chance to actually put in the final piece of the implementation, which is that we need to have some way of sort of passing that information into the system, the render system, and we don't really have that yet. So we need to kind of go in there and just make a little conduit so that we have a good way for code that wants to control the camera's orientation to be able to do so. Ooh, as I spill things all over the place. Sorry about that. This is why it's very bad, for those of you who are wondering, it's always very bad to forget your water bottle, because my water bottle has that nice seal on top of it that doesn't let me spill things. Sorry about that. No components ruined as far as I know, but I guess we'll find out. All right. So that's really all we're trying to do today, is we just want to put that rotating camera in. And again, the reason for the rotating camera is not so much for any particular game design reason. We don't necessarily think that we're going to have to rotate the camera in the game at all, but I do want to be able to rotate the camera for debugging purposes, because as we basically next weekend will pretty much be all this, as we move all of the code that uses the renderer, now that the renderer understands 3D, as we move all the code that was previously just sending out 2D sprites to be able to start sending down information about three-dimensional sprites, we're going to want to be able to see where we're messing things up, because it's easy to have a bug in 3D that doesn't look like a bug in 2D necessarily. Well, it will look like a bug, but you won't be able to tell what the bug is, because all you can see is the 2D projection of it. And being able to rotate around is very important, because it allows you to see more information, and you'll spend less time debugging if you have better information. That's just generally the way it goes. The more you can visualize, the less time you'll have to debug. So let's go ahead and remind ourselves where we are. Right now, we look the same as we normally do. Again, sorting is disabled right now, so we get the flashing. But otherwise, everything's in the right place. And that is with the 3D transform going through OpenGL now, rather than going through our code, which it used to before we started this changeover. And then if we go into render group, there's a part where we do set camera transform. You can see it here, where we pass in the information like whether or not it's supposed to be orthographic, what the focal length was, and what the camera P is. And what you can see about this function is really, this is where we would like to start putting that information, where we've got sort of the push clip rect and the camera transform are sort of separate things. And really what we're doing here very much so is we're collapsing these things down. Now, as you remember from yesterday, we made it so that you could pass an entire matrix down with the clip rect. So really the clip rect is actually really the camera in a sense, right? Now it not only encapsulates what render target you're targeting, what the rectangle is that we're clipping to, but it also encapsulates how all of the information that's going down is going to get transformed. So we don't have to rename this right now. I mean, we know that. But this is definitely something where we want to rename it to something other than clip rect, because it's doing a lot more work than that now. It's sort of like the render setup. And it's going to be something that if it was called clip rect all the time, if someone was trying to read this code later, might skip over it thinking it only had to do with clipping, but actually now it's a lot more than that. So you can see here we've got the full 4x4 projection. And remember, because that's a 4x4 matrix, not only can it do the actual projection, but it can actually do everything necessary to put things into camera space as well, because it's a complete transform. So that's pretty nice. And what that means is that with our render entry clip rect, we should now be able to make it so that push clip rect and set camera transform are basically the same thing. And really, they're just accessing different parts of that piece of information. So that's kind of what I want to get us to here. And so what I'm going to do is I'm going to go up to push clip rect, and I'm going to try to pull that information down, or rather push this information up might be a better way to say it, so that we have a more coherent way of working with this. So I'm going to slide begin render group and end render group down because those are kind of primal, and those have to set up an initial camera transform, which is just whatever it is if you don't set anything. It's unclear whether we really want that. We could make it so that you're always supposed to actually set something, but for the time being, we'll leave it that way. I'm going to grab these push clip recs out of here so that we can see them all at the same time, and I'm going to come down to the rendering code here, and I'm just going to put them all in this one place so we can take a look at them. I'm also going to switch to the other window so my head's not in the way while we're looking at it there. All right, so you can see what's going on here. We've got a couple different things that are happening. Basically, we've got two push clip rect calls that do nothing other than prep for the other push rect call. Like this is the push clip rect call here that actually does the work. These two are just ways of specifying the clip rect in some other way. And so this one is just a light way of saying, hey, I want to pass a rectangle too with a z coordinate. This one is saying, all right, I've got a full 3D offset and then a dimension and then an object transform, and I want to transform by the object transform, right? And then finally, you get to this one, which is actually the one that does the work, and that's just taking integer coordinates, what the render target is, and what the focal length is. And you can see that playing out here, right? OK. So what we want to do now is we want to take a look at how people are using these. Because we're going to have to fundamentally change that a little bit, I think. Because what we want to be able to do is when we push a new clip rect on, we may want it to be in reference to an old clip rect. And we may want to copy stuff out of it. And here's why I say that. Because there's two ways that people might want to be using this function. One way that people might want to be using this function is just to create a new clipping rect, or just to create a new camera transform. And they may not be trying to change the clipping rectangle or the camera transform. So we kind of want a way of storing what the last camera or the last clip rect was, so that when people want to just modify one or the other, they don't have to necessarily remember what the other one was, right? So that's kind of one thing that I'd like to be able to do here. And so we need to start making it more aware of that in general. That's going to have to be something that we're taking a little more seriously. Furthermore, we're probably going to pull out this projection creation call, and we'll probably make it so that both perspective and orthographic, we can stop probably looking at these all together, the false true dichotomy where we're passing those down and all that sort of stuff, and just make a matrix, because we can do an orthographic projection with a matrix just like we can do a perspective projection with a matrix. So this will really unify a lot of our code and make it so that we don't have as much special casing, which is really nice as well, right? It's just kind of cleaning everything up. And again, the more we sort of push towards a standard 3D pipeline, the more it cleans things up, because the 3D pipeline is something that's been refined for generations now by people who have been trying to make it more and more consistent, cleaner, and whatever. So typically, the 3D pipeline tends to be a very clean way to do things, primarily just because people have spent so much time getting it right. If we had not had the whole history of 3D transforms behind us, we probably wouldn't have thought of using a 4x4 matrix with the homogeneous coordinates to do, there's all this stuff that we wouldn't necessarily have just thought of the first time out, right? So we're really leaning on past design in a sense here, because there's been a lot of people who've worked out a lot of good ideas there, and we're just being able to use them. So that is a nice aspect of the 3D pipeline that was never really true of the 2D pipeline. Pipelines were always just a lot more ad hoc, and so that there is that. Anyway, so I'm going to go ahead and take a look at push clip rect here. I'm going to look at where it happens. So these are all inside render group. So if you look, there's really only two places we do it. There's the push clip rect here, and then we've got push clip rect here in the debug code, and again here. And if I look at this, you can see that really these are just orthographic push clip rects right there, just trying to restrict to a part of the screen that's what they expect. So the only orthographic one is here. You can see it where it's trying to specify a new alpha floor rect. It's not actually doing anything with the actual clipping, right? So really, this is more of just setting the render target is all this is. And so again, you can kind of see that each of these is really doing its own thing. These are really push clip recs. This is really push render target. And so that's why I say, we kind of want to start to disaggregate those because again, now we're also going to have the people who call perspective and orthographic. They're also pushing clip recs on, but they're pushing them on for the purposes of camera transform. All right. So what we can see here is this push clip rect is just a push render target. And so I think what I'd like to do is actually just make it be that explicitly and not have it set the clip rect at all. So this is more of a push render target. And here we have the render group, which we need. None of this stuff would we actually need. We would only need the alpha floor render target. And furthermore, if we were to do that compilation step, I don't know that we would now need, like, for example, the draw buffer. It may be that that was the only reason. Yeah, and you can see that, again, this is just a nice way to start pulling out some of that code complexity that just shouldn't have been there. And I think I mentioned this back when we were doing it as well. I had started trying to clean some of those out. And you can see that if we just get rid of that, the only reason that we ever even had to pass this into this routine, the only reason update and render entities was aware of the draw buffer at all, was just because when it was pushing the render target down, it needed to know that, right? But it never really cared what the clip rect was. As far as it was concerned, you could have just inherited the clip rect from whoever set it up beforehand. And it was just forced to know what it was because it had to pass that down in addition to the render target, which is what it was actually trying to set. So I'd like to, again, that's why I'm trying to move to that sort of system. That way, when we call update and render entities here, we can get rid of the draw buffer. The draw buffer doesn't have to be there anymore. And if we take a look back, that change has a positive cascade effect all the way back because you can look at simulate now. Simulate doesn't need to take the draw buffer anymore, so that's nice, right? So yeah, it's just one more piece of complexity that nicely falls away. And that's really nice. So if we want to add that in here, so that's another aspect of this saucy gentleman, where it's going to be, let's see here, that's a U32 that's going to get back, where it does a push render target. And there we go. Don't actually know what the render target in this is, U32. So there we've got a push render target. This is not implemented yet, so we're going to have to do something about that in a moment. But that's our push render target call. If I compile here, we're in good shape. And so then let's take a look at some of these other ones. So in push clip rect now, what I'd like to do is in these other functions where we're passing it, I'd like to get rid of the render target because the render target is now no longer relevant. Similarly, the focal length and those sorts of things shouldn't really be relevant. So I'm just going to temporarily remove those, right? We're going to say, let's pretend we had that as well, kind of a thing. And similarly, here we would get rid of that too, because we wouldn't be passing it to a function that doesn't need it. So that this way, these would go back to being actual push clip rect, and this would be something more like push camera or something like this, or push render setup. I don't really know what we want to call that. I don't know that there's a really good name for that bundle, which is the clip rect, the render target, and the camera transform. But I guess I'll call it push setup for now. So when we do a push setup, what I want to do is have this take, I guess, everything. So it would take the clip rectangle that you're going to use. It'd take the render target index. It would also then need the matrix that we're going to use. So this would be the projection matrix, and it would just copy that in there. So this stuff here, where we're creating this projection, where we have the safe ratio and the focal length and that sort of stuff, that stuff wants to come out, and that would be going into these camera transforms more explicitly here. We'll deal with that in a second. But then in here where we're doing the rect, what we want to do is we want to go ahead and just capture that projection matrix, whatever we are being given, and leave it at that, right? So now in the push setup call, the primary thing that we need to be able to do is get that information as we go. And I'm not sure exactly how we want to do that. We might have to think about that a little bit. We do have this concept of the camera transform. You can see the camera transform here where it's got orthographic focal length camera P. And I think really what we want to do there with that camera transform potentially is the camera transform may just now want to be a 4x4, right? We may not really want camera transform to be an actual thing that people think about anymore. I'm not sure, but that's probably the case. So what we would be storing for now is like last projection or something like this, right? And we'd have last render target. And the reason that I have that is just because I'm going to use it as sort of an accumulation, as a holdover, like a rolling sort of situation where we just say, hey, every time you set one of these, we'll just keep that as the current one so that if you set something else, it's just assumed to have a little state in there. And you don't always want to do stuff like that because sometimes you can forget or it gets kind of hairy what's what and when. But in this particular case, I just would rather do it that way for now because typically the way that our render stuff is set up is we set a state and we do a bunch of stuff with it. It just turns out to be a nice way to compress the amount of information that you're sending down. All right. So here's the render target index. I want to say last render target, like so. And here this would just be last projection. And that way, when we're doing that, off it goes. Whenever we call one of these push setup calls, again, since I don't anticipate this being called frequently, I'm not super concerned about the efficiency here, which is why I'm OK copying giant matrices around. If I was concerned about the efficiency, I might want to be a little bit more careful here if I thought we were going to be pushing setups a lot. And so it is worth noting that is just, it's something to be aware of, if that makes sense. So what I want to do here is just say, all right, the render target index, I want to snap that out to the last render target. And similarly, the last projection, I want to snap that. And I'm also going to want to snap the rectangle 2 here. So I want to do last clip x equals x, this sort of thing. And that's about it, right? So given that, then when other people do transforms, they don't have to do anything like looking at the screen dim or pixel height or any of this stuff. They can just use whatever the last clip rect was, right? So if you want to push a clip rect, you can push a clip rect, and then you can also set the camera transform if that's what you want. But you can also just set the camera transform. If all you're trying to do is set the camera transform, you can do that as well, and you don't have to worry about it, right? So similarly on here, I can say current clip rect index. I can do a push clip rect when I want to do the render target. And when I call that, I can just say, like, OK, the render group last clip x, last clip y, last clip w, last clip h. And then I don't have to deal with any of that. And I can say the projection matrix is whatever the last projection matrix was. So the only thing I'm really doing here is passing down that render target index. Right? That's the only thing I actually want to do. What are you complaining about? Oh, is that actually passing? OK, well, that's something we can deal with this. We can deal with that in a moment. There's too much stuff here. All right, so that needs a semicolon. And OK, here we go. So let's see, push setup. That all looks fine to me. Push clip rect pushes the clip rect as we want it to, and that's all good. And set camera transform. So let's take a look at these two routines now. So set camera transform and push render target. Push render target is basically done now. Set camera transform is not. So set camera transform, I'm going to stop that from doing anything with the screen dimensions, since it doesn't actually need to do that for any particular reason at the moment. So we can get rid of those. And it really just needs to take a look at these for doing those aspect ratio correction. So here's that creation of the projection matrix. Here we are setting information about the camera. And what we really now don't need to do is remember this stuff specifically, right? So basically, like, we don't need that. We just pass in the focal length and use it is all we're really doing here. When we're saying whether or not it's supposed to be orthographic or not, that's just going to be an operation that has to do with how we're going to create our projection matrix. So I can do an orthographic instead, and I can still pass down that same ratio that we're using for aspect ratio correction, because we're going to want to do that. And then we can make a routine that'll create an orthographic projection and use that. Looks like we're doing that way. There we go. OK. So we've got orthographic, and that's all good. We've got projection, and that's good. But now we have to deal with the part that's actually the thing that we wanted anyway, which is that when we do a set camera transform here, rather than just having a camera P, we've now got this way, like we saw in the math routines, we've got this way of creating a camera transform out of axes and a location. What I'd rather do is just say, what's the actual camera transform, right? Just tell me what the camera transform is, the whole thing, rotation and position, instead of just giving me position. Then, when I come through here and create the projection matrix, what I can do is I can take the camera transform and say, hey, apply the camera transform first to the points, right? And then apply the projection matrix or the orthographic matrix, right? And so perhaps more properly, we could do it this way and say we have an M4x4, which is our projection only, right? And our projection only gets set to one or the other, and then I just take whichever one we actually picked. Oops, there we go. Whichever one we actually picked, and then I multiply it by the camera transform. And again, remember, transforms, because of the way the math reads out, and we did ours in math order, is the rightmost transform occurs first, which is what we want. We want to put everything into the space of the camera first, and then we want to apply the projection, not the other way around for obvious reasons, because the projection would be totally wrong if we were applying it before moving the world to be centered around the camera. So that's really it for what we wanted to do. Now we just have to actually push the clip direct on. So here's that push clip direct call. And basically what we're doing here is, again, passing all old information except for one thing, which in this case is going to be our projection. There we go. So that's all well and good, but now we have to clean up sort of the fact that we pushed this to the outside. The code that's calling us is going to now have to be aware of that and do the right thing. So now we can see when we call get render entity basis P, one of the interesting things about this is now we actually have in this get render entity basis P, all of this code is kind of now not necessary, right? Like this code is actually sort of meaningless for us. So when we call get render entity basis P, we're just doing a transform on P. And most of this stuff just simply isn't necessary. All of the stuff is happening in the projection matrix. We certainly don't need to do really any of, pretty much none of this stuff is really all that necessary. And so a lot of this function may actually go away entirely pretty soon. I'm going to leave it on there. You can see the camera transform coming in here. And that camera transform now, you can see that it's just using the position out of it, the X and Y and the Z. And we don't want any of that anymore, right? We don't want any of that anymore because we're already accounting for that inside our regular transform. So we don't need any of that and really just don't need to do it, right? So we want to go ahead and take all of this stuff out and start to collapse this function down even more, probably get rid of it eventually entirely, right? So it looks like that now. Does not actually need any of this information. When we look at the orthographic thing, we're going to have to, again, have that be a little bit more clear, but that's going to happen almost entirely in the matrices anyway, so we should be good there. And so here we now no longer have to pass any of that. We don't need to access what the camera transform was because that's not relevant anymore. Okay. All right. So then when we get to things like unprojection, unprojection is going to be a little bit trickier for us now. The reason that it's a little bit trickier for us is because we have an actual projection matrix that we're using, right? And because we're using an actual projection matrix, what that means is we need the ability to invert our projection matrix, right? We need the some way of being able to undo the effects of the projection matrix when we want to for unproject, right? So this part is still going to be roughly the same, right? This part where we do our unproject in terms of correcting for aspect ratio and that sort of stuff, we're still mostly going to be doing that, although not exactly, right? Because of the order of the operations. So I guess I would probably say let's push this on to the let's push this on because this is kind of going to be a topic in and of itself. So what I'd rather do here is just say, all right, let's just patch this temporarily to not be a problem. But then afterwards, we will have to do the real work there. So all I've done is just remove it. This is not correct anymore, right? It's completely wrong, but that's okay. And let's go ahead and that one in there as well. Who knows? All right. So here we are in push clip rect. And at this point, again, we shouldn't have to pass that down. Presumably, that can just be used straight. And what is the problem here? We need to pass that as an address. That's all good. We don't have orthographic yet as a thing to make, but that's OK for the time being. Push clip rect, in this case, we need to pass the address of the matrix again. That's going to be true down here as well. And 7 arguments. It's push setup, that's why. I renamed it. All right. So set camera transform in both cases now is not really, I don't even know that we really need that because now you just pass the camera transform directly and you don't even need to pass the ortho or not. Now that I think about it, in some sense, well, I guess you still sort of do. I mean, what we could do is have this pass the entire thing, but I guess I'll leave it this way for now. For now, we'll see. So when we call orthographic or perspective, really those could just be calling the other function now because they don't really need to do anything. They really want to create a whole camera transform probably. So what I would say is we'll just get rid of those, let those error out higher up the chain, and deal with it there. We do need to have that ability to do a projection, I mean an orthographic projection, so we will have to make that happen, but for now we can ignore that temporarily. So here's our push setup call. So when we're doing a push setup in a case where we are trying to set sort of a default case, we can also pass an identity matrix here, which does no transform for the camera, which is presumably what we would want at initial setup. And it looks like I missed an argument there. All right, really starting to not like the fact that my head is in their way. So let's see. So we've got group 0, 0, so that's x, y, width, and height. We've got the render target, and we don't need the focal length anymore, obviously, because that's rolled into the camera. Projection, which we're saying is nothing right now at all, right? Yeah. And no one should really ever be using this anyway. So in theory, I don't know, maybe the right thing to do is actually to push some thing that doesn't render anything. I don't know. Because everyone's supposed to set up a camera, even the orthographic stuff, before it's used. All right, so in update and render entities, here it is trying to get the camera P out of the camera transform. I'm not sure what that's being used for. It looks like that's just, so that's a hack already, actually. You can see that being a hack right there. And that's just, again, for that fog, that alpha and fog sort of split up, if that makes sense. And again, I don't think we really want any of that anymore. In fact, all of this can go, because now that we're passing actual 3D stuff down to the renderer can just split things in half at a particular Z and make that alpha in. Yeah, this is all pretty much not necessary anymore, and we want to get rid of it all, basically. It's unfortunate that this is such a big change, because of course it means our debugging time is going to go up, but that's okay. At least it makes things cleaner. So if you take a look at all this stuff and typical floor height, all that stuff, we don't really need any of that anymore. That can all go. So what we can do is we can just delete all of this stuff, and we can literally just get rid of all of this stuff. None of this is even remotely necessary anymore, because since we have Z in the back end, all we have to do now is just look at the Z in the back end and color what we want and clip what we want based on that Z. And so that's not going to be particularly difficult. And again, it just cleans up a lot of stuff. This is why I like the 3D pipeline better. But a lot of times it's important to kind of go through an exercise like we did with the 2D pipeline to see how hard is it to do this way versus doing it the standard 3D way, and now I know. So anyway, inside the render group, if here, this is just getting different clip recs for these guys, which we don't really need at the moment. Again, the render target, I think stuff can actually just be done, can be handled inside the renderer entirely. So all of that stuff is probably fine. And absolute Z layer, I think all that stuff is just not necessary. Let me go ahead and see where that actually gets used again. I don't think, let's see. Camera relative ground Z. So getting the ground point is going to be something that we probably would need to know, I guess. That really shouldn't be something that was done here. I think this should just go away as well. So I think the particle systems, they were actually having to use this information, which again is just really ugly. So that's great that that goes away. And in fact, the chunk can also go away, I think. Let's take a look at that. So when this gets a bitmap push on the transform, it needed the chunk Z and the floor Z. That's gone now, right? So those don't need to be there anymore, and that's pretty good, I think. All right. So let's see. Yeah, if we don't need those anymore, that's pretty fantastic. So we can get rid of all those. and just not need them anymore. And inside those transforms, in fact, I'll just get rid of those here. We don't need the sorting or the floor Z or the chunk Z anymore. So let's get rid of that. And we'll get rid of this. And that. And I don't know that entity Z layer is something that even needs to be there anymore either, but like I think that's just not necessary. Yeah, that's just not necessary. It's not used in simulation. That was only a rendering step. So this is all fine. And while we're in here, right, we don't need the sort barriering or any of that. We don't need the layer index. Yeah, we don't need any of this because this will all be just transformed. This will all be stuff that's color, that's all colored based on where you are in actual Z. So I think we can safely nerf that for now. In fact, even the color stuff we can nerf for now, because again, that's just not a place we really want to put that anymore now that we have so many other options. And none of this stuff is necessary. All right. So that's all good. Let's see what else we got here of stuff that I need to clip out. So this is transform floor Z. Doesn't need to happen anymore. And orthographic. Chunk Z. We're going to have to do some stuff here. We're going to have to figure out some ways that we want to have the orthographic stuff work for the debug system, but we'll get to that when we sort of flesh that out. There we go. Okay. So this is still the same. It just doesn't need to take the render target anymore. And similarly, I don't know if that render target is even necessary anymore, because I think the only reason it was there was just for that one reason. So that can go away. And now we've got just us calling the orthographic or the perspective stuff, and now we have to fix that. So when we call perspective here, what we need to do is create a camera transform, and that camera transform then has to be passed as a 4x4 to the render group itself. So here's that set camera transform call, which is what I'm going to be calling now. Also, similarly, we would want to set the clip rect, although the clip rect will be set by default to the whole screen, so we probably don't really need to modify it. So when we call set camera transform here, and we have the camera focal length, that's going to stay the same. It will not be an orthographic projection, and we will want to create the camera 4x4 like so. Oops. So in this case, the camera transform here, we don't have any of those axes yet that we were looking for. We don't know what the x-axis is or the y-axis or the z-axis for any kind of rotated camera. So first, we're just going to pass in basically an identity, but we are going to have that offset to maintain so the position is correct. And we're going to pass that down to the camera transform. Then inside oh, whoops. When I did set camera transform, it looks like that should be a pointer. I don't want to copy all those on the stack necessarily. Although, you know, maybe that's okay. Depends. I haven't measured it. There we go. Okay. For our layered scene, we don't need to move the camera or anything. So in this case, it would just be the identity matrix again. And so I can just say, pass that, and call set camera transform. And again, that's going to be perspective, not orthographic. So then we just have one last person here who needs to set the camera transform. And this one does need to be orthographic. And so we just need a way of dealing with that for now. Again, I'm going to not do anything particularly clever here because we haven't really gotten around to dealing with any of that yet. So now the only thing we don't have is a thing that does an actual orthographic projection. And again, that's not something that I want to focus on at the moment because it's only for the debug code, which we do want to enable, but at the moment we are going to have to live without. And when we take a look at the perspective call, which is oh, did I just call it projection? Ah, that's dumb. It's a perspective projection. So yeah. So for our orthographic projection, which is different, really what you can see here is we don't really need to do anything with the focal length, right? We don't care what the focal length is at all. So really, all we have is the aspect width over height. We're not trying to put anything. Remember, this was the thing that moved something into the W coordinate so that when the divide happened, it would normalize itself out. In this case, we don't really want to do anything here at all. And we don't really necessarily know what we want in the W coordinate. So for now, I'm just going to put 1 there. And so we'll just sort of leave this be. And we may want to do a little bit more with that later, right? Because we may want our orthographic projection to do other stuff there in terms of sizing the world, however it's going to size it, beyond just aspect correction. So I'm just going to say, look at orthographic. Re-enable. Oh, look, fix unproject is already on there. All right. All right. So our orthographic projection will be good enough for the time being just as a stand-in, but again, we are going to want to maybe take a look at how we're doing that and what we actually want that matrix to do beyond just not the perspective divide. Like all I did was essentially like nerf the perspective divide to make sure that it didn't happen, but that's it. All right, so we've made massive changes everywhere, so probably none of this is going to work. That's okay. We're just sort of getting things into position. And we'll step through this now and start to try and clean out what needs to happen and what what needs to get fixed in order for us to see stuff on the screen again. But we're definitely getting closer to having the pipeline be reasonable. So if I go back to, let's see here, Handmade world mode, I just want to set a breakpoint. Here we go. So here where I call camera transform, I just want to take a look that this stuff is actually somewhat reasonable, if that makes sense. And don't forget, we are actually calling get camera rectangle at target here. And that may be broken because we didn't fix unproject and stuff yet. So there is that. And we'll check that out as well. But I just want to, before we go any further, want to take a brief look at this code to make sure that it looks at all reasonable to me before we go any further. So here we are inside our push setup call. I want to make sure that all the stuff in the group got set properly. It does look that way. Here's our screen. That is the size of the screen at the moment, so that's good. Here's that projection matrix. Let's take a look at what that looks like. I'm going to slide this over a little so we can see more explicitly. Here's that matrix. 1's down the diagonal except 0. Here is the aspect correction factor on the Y, which is what we want. Again, it's the inverse of what you would expect because we're going to the unit cube, not away from the unit cube. And then we've got our perspective divide quantity here, multiplying the z. And that's really all we need. So that all looks clean. When we set it all up, let's see and make sure that it gets into the rectangle that we actually created. It should be set to all those things as well. Just want to make sure. Again, looks good. That looks like what we want. So we're at least pushing that information on properly. We're getting that into the current clip rect. So that all looks reasonable to me. And I think that's fine for the camera transform. Now when we do get camera rectangle at target, this is probably broken because again, we're not doing that projection correctly. But the result is not awful. It's just not good. It's not going to be very large, right? And so I don't know how much that will affect us here. The world camera rect, let's see what the screen bounds are here. Yeah. So I don't know to what extent that will create a problem for us testing this, whether we're going to need to actually fix that function first before we debug any further. That may be the case. But I'm just going to go ahead and take a look at the sim region and see. It does look like it grabbed 400 entities, so something's getting grabbed. So in theory, we should be able to debug it. So since this came up in the middle, and you know how much everyone who watched the stream knows how much I love modern software and how great it is. Like I love the notion that somebody thought it was okay to pop this up in the middle of like a user's daily work. Thought that was good. But I want to show you the other really great part about this, which is it's like, hey, yeah, you know, it sounds great. I'd love to upgrade. Let's do that. Let's get that new driver. I'm excited. I can't wait for it. Hit me up, AMD, with the new driver. Pretty great, huh? Like, they routinely interrupt my workflow to tell me that there's a new driver, and when I try to install the new driver, they tell me that it doesn't have anything to install. It's great. Fantastic. All right. So here we go. Check for joining new players. That's not relevant to us, obviously, and simulate is not really what we want, but we have to get into it because it's where we do our update and render, which is what I actually need to access. So here we are in update and render entities. We're going through here, and I just want to, again, take a brief look at the render activity here, just to see if we ever actually call anyone. Because it's possible that that sim region made it so that nobody is actually active, and that they're all kind of outside of the active range, because that sim region is wrong, because the unproject is not implemented. So let's see, where are we actually pushing our bitmaps here? That's going to be down here, right? Do we ever actually get there? We do. OK, good. So here we go with the push bitmap call. In the push bitmap call, we're just going to verify that we actually got one. OK, so we got to wait till we actually get to a push bitmap. There we go. So I'll come in here, take a look at when we get the bitmap dimensions. That's going to give us back our coordinates. And this is what I'm primarily concerned about here, that z. You can see that in there, right? And so what I'm curious about now is I would like to know, is that z compatible with what we ended up setting in our render group, right? So our group last proj, here's what got set. And what you can see there is I'm not getting any displacement, right? You remember these coordinates here, those coordinates are the camera's, the inverse, the undoing of the camera's location. So we're not rotating the camera yet. So we would expect them to be straight negatives of the camera position. But instead, I'm just getting all zeros there. And now I think about it, when I step through that, that is what was happening. Does that mean that the camera offset was 0? It does look like it was. So that's not a useful camera offset. So let's see, was that just because frame 0, it hasn't gotten set yet? Because it hasn't had a frame to actually pick up the change? If that's the case, I'd like to see it. Yeah, so there we go. That's better. Z equals 8. I think that's what we want. So now when we set the camera transform, now let's go through and take a look at that push bitmap call. Oops. Got to actually reset that breakpoint. There we go. And so inside here now I should see, and that's what I wanted, right? I wanted that -8 in there, right? Because that's, if the camera is 8 up on the z-axis, then that means during transforms, everything else should get pushed 8 away, right? It should get pushed 8 down the z-axis, the other direction, towards further away from the camera, right? And that's exactly what we want. So that is what I wanted to see. That's good. I'm going to step into the get bitmap dim call here just so I can see what's going on there. It's the entity basis p function that I would like to take a look at. Again, distance above target and floor z. This is all zeroed out now. And that's only in render debug mode that we have that. And we can roll that into the projection matrix too. So we'll be able to get rid of that. The height off floor, raw z, ortho. Let's take a look at any of this stuff here. Take a look at that result. So the result of z equals 0 is a good result. That's a reasonable result. These x and y's are way off, pretty far to the left and down. But the z is at least in the right place. So that's good to see as well, just in terms of things that can be wrong. And then when we push the render element on there, we should expect everything to be clean there. On this render entry, I guess we can't see the header, unfortunately. But I guess I could try to what's the name of that function? I'm sorry, structure. Render group entry header. That's what I wanted. So I just want to double check if I look at the render group entry header. So I know that this entry is here. So in theory, if I just take that location and call that a render group entry header, that won't be anything meaningful because I'm looking at this data. But I know that the render entry header is just sitting right above it. So I should be able to do a -1 on that and get the actual one, right? And here it is. Type 0 is a bitmap. Oops, no, don't change that. Type 0 is a bitmap, so that is what I expect. Cliprect 1 is also what I would expect, so that's good. That's what I wanted to see. And I just want to make sure that is actually the last cliprect that was pushed on. Let's verify that that's true. Yes. So that's all good as well. So all of that is good. Let's see here. So it looks like here, where we're doing store color, I should also just double check that we didn't, because we nerfed those colors. I should also check that our pre-multiplied color is not meaningless. So that's good. 111 is what I wanted, so that's all good too. Because otherwise, we could have something that was alphing out all of our graphics or something like that. So I want to make sure that that's stable as well. All right, so we're pushing all of that stuff on there, and all of those bitmaps are coming down. But for some reason, I'm still not seeing them on the screen. So I'm going to jump over to the OpenGL side here and see if I can get a better picture, perhaps, what is incorrect there. So I'm going to come down here. We're looking at the first clip rect index, which is clip entry index 0. Who got pushed with the 0 clip rect? I wonder. Oh, it's just the clip rect itself. Okay, that's a waste of time. We should probably short circuit the, if the entry itself is a clip rect, then you don't have to care. That's a good point. I'm going to go ahead and put that in there. Never thought about that before. But now that we do have the clip rects coming through here, when we do this check, we probably want to check that the header type render group entry type. There we go. So this is just saying, hey, if this is a clip rect, then we don't need to set up the clip rect for a clip rect because it doesn't draw anything. So we want to make sure that the header type is not a clip rect, and then it's all fine. All right, so let's try that one more time. I'm not sure why that. If the header type is not one of those, that should not have really had any effect at all, really. Right? Oh, I put that in the wrong place. That's where I actually wanted that. There we go. Sorry about that. Mental mistake. I was only trying to get rid of this clause, not this one. All right, much better. So now I just want to go ahead and stop in here, and I should see the first one should be clip rect index 1. Yeah, because that's the, no one should be pushing anything on clip rect 0. That would be a mistake. So here we go, we get out the clip rect, and again, this clip rect should look like the one we inspected before. It should be that one. So here's the projection matrix, which is what we expect, and here's the screen region. So we need to transpose this first before we load it, but otherwise that's fine. So just going to flip this around, and that's going to load it up. I guess I should verify that it actually does look that way. And yep, that looks like a nice flip to me. I will say, wait, why are we getting a -26 here, though. That seems odd to me because that should have been zeroed out. So that's a little weird. I would be interested to know how that happened. How did that happen? I think we should go inspect that a little bit further just to make sure we know what's going on. Is that what we would expect to have happen there? Let's see how that occurred. I'd like to take a little closer look at that. I didn't pay attention to that before. So let's just make sure that that math checks out before I continue down the path I was about to continue down. I would like to see what's going on there. So let's see. Here's our set camera transform call. And let me go through once so we're at the right camera. So here's our set camera transform call. Our camera transform itself should look like what we expect it to look like. One's down the diagonal and just the position. That is what it looks like. And so our perspective projection let's make sure that looks like what we think. That is what we think. And so let's go into the multiply and make sure that the multiply looks right to us. So here is us creating the individual columns. We can actually watch these happen, right? This is it producing the 0, 0 element. Here it is producing the 0, 1 element. Continue on, and so here's it producing the final element of the row, right? Go, 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 go. Doing its little multiplication. Should probably put these on here. All right. So here we are on R33, right? And so what we would expect to see here, let's just figure out what we would expect to see here first, and then verify that it's actually what we think it should be. So we're multiplying A times B, and remember that means that A is the one that's appearing on the left, and B is the one that's appearing on the right above. And we're trying to multiply this, so it'd be this row times this column, right? So I guess I do actually believe that does look true, right? The -8 should multiply the 3.333333.2.5 here, right? And that's where we're getting that term from. It's from here. So that is actually correct, I guess. Yeah. And now I think about that's fine, because the W coordinate there, what's going to happen in the W coordinate of the matrix down at the bottom there, is, the 3, 3 element. That's essentially going to be an offset to the W, which is what this is, right? We're saying that the camera gets pushed back that much, so we do need the W to be offset by that much so that the divide is that much more. So I am okay with that. That seems reasonable. And off we go. So let me go back to what I was doing. Just wanted to make sure that that was right. Let's go ahead and take a look at one of our actual bitmap calls. There we go. So I just want to take a look at what these values actually are down here to make sure that they look sane to me. That's all I'm doing right now. And yeah. So here's the values we're actually sending down. X-axis, y-axis, min p. The x-axis and the y-axis in this case look totally reasonable. They're just scaled, but that's all they, there's nothing weird about them. The minimum p, it's kind of all off to the left and down. Let me just see if in general, is that where everything is? So you can kind of see that everything that we're drawing is far to the left of us. There we go. Now we're getting some stuff that there was a few things that were close to us there. So now we're drawing things that are to the right of us as well. Still below us. There's now some stuff that's, well, we still haven't quite seen anything that's right on target. But I'm just curious, I'm just checking to see if there's any sort of... So that looked pretty reasonable. So these numbers look pretty reasonable though. So I'll be honest, I don't immediately see any problem there. So I do wonder... I do wonder a little bit if we have to look at the near and far clip plane now as culprits. So let's talk about that, because we haven't done anything to process the z-coordinate, and that may be a problem. So let's take a look. So what you can see here in our perspective projection, which we've been working on, is that we set up our divide to do the divide that we wanted to do to produce the x and y coordinates that we thought we were going to produce that would match what we were previously producing. However, at the moment, we don't do anything with the z-coordinate. We just pass through whatever the z-coordinate actually was. What I'm concerned about is that the clipping that happens in OpenGL to the near and far clip planes may be causing us a problem. I believe that happens with the z-coordinate, although I could be wrong about that. We could go double check the pipeline stuff. So I'm just curious to know if the z-coordinate is a problem there. I'm just going to check it real quick. Okay. All that would do is knock out the z-coordinate, right, so that it wouldn't actually push anything into the z-coordinate, if that makes sense. So I just wanted to double check what was actually happening there. All right, so let's talk about the near and far clip planes, and let's just go try to verify whether or not we're doing anything particularly wrong with how OpenGL wants us to produce points that conform to what it's going to clip to. Because remember, we've got that notion I kind of went over a couple weeks ago about the clip space and the unit cube and all that sort of stuff. We have to make sure that we're playing exactly by the GPU's rules here, which again is not necessarily what we had been doing when we created the rules ourselves. When we made the pipeline for the software side, we didn't have to play by the GPU's rules. We didn't have to even know how the GPU conceptualizes things like clipping. Now we do, and we have to keep in mind as well that in addition to clipping off the left, right, top, and bottom of the screen, OpenGL will also clip things that are far away and things that are too close. So it's a full clip in all three dimensions. And so if we're producing coordinates that are not kosher in any way, then we will have a problem. So I want to, again, I have to eliminate these things one at a time in order to find out what the problem is with our transform process, right? Excuse me. So let's just double check how OpenGL wants those matrices set. Hoping I could find one that's got a reasonable drawing of it. That's not it. That's not either. This is what I want, but man, it's not formatted right at all. I just want one that's formatted well. good enough. So here you can see, right, where we're getting this. This is what the GL utility library, the one that comes with OpenGL, this is how it sets things up. And you can see how they do it. It's not that much different from ours, but it does a couple things slightly differently. So in the top two parts here, they basically do what we do, but they do things slightly differently. So rather than use focal length, they use field of view and Y, which is basically an angle measure. It's saying how wide you want the field of view to be. But they have the aspect ratio correction. They also do the aspect ratio opposite from what we do. They do the aspect ratio of the width to height in the X, right? So where is our... yeah, and we were doing that in the Y. I wonder if that means... That's weird. Do we... I thought we worked out which way that should be going. And this looks a little bit backwards from us. Aspect ratio is the ratio of X to Y. And you can see the aspect ratio here. Oh, because it's 1 over. They must be missing a 1 there. Yeah, you can see they're missing the 1. I'm like, they've got it backwards. They don't have it backwards. They just... There's supposed to be a 1 there. And there isn't. Right? So they do it exactly the same way we do, right? Except we put it into a Y correction, and they put it into an X correction. So that's why they had to invert theirs, and we didn't have to invert ours because they put it on the other side, right? Field of view and Y we're not using. We were using focal length, so we don't actually do that the same way, if that makes sense. Field of view and Y is a reasonable way to do it. I don't know that we want to do it that way, so I'm going to stick to not messing with that part of it, but we can leave that for later. So anyway, I think everything else is fairly similar. 1 over the focal length goes down to get our W divide to be what we wanted it to be, right? And I'm pretty sure we checked that math to line up with the math that we were using previously. And so that is similar to what they're doing, although they don't actually change that coordinate at all. So they take the Z directly, if that makes sense. They basically say, hey, whatever the Z comes in, we're not going to change it at all. We don't modify it by the focal length. We just have it, we just directly set that value, right? I guess the way to think about that, and I guess I don't know that I have any particular... So here's what I'm going to say. I think this probably wasn't a 1 here. I think this was probably an F, if I'm just guessing. Because I think what they basically did was they put the multiplier in here for F rather than putting it down here, right? Because what we did is we stuffed the focal length, which is equivalent to the field of view. It's not the same value. It's not the same way of setting the value, but it's a similar computation, right? That value that controls the field of view, which the focal length does, just in a different way of specifying it, we put that so that would go into the computation of the denominator of the divide, but they left it in the numerator of the divide, right? So we could do that as well if we wanted to, right? All we would have to do is multiply it into here, right? And that would do it. I don't know if there's some reason why we have to do that in order to maintain clip space properly for how they want it lined up, right? Because looking at their matrix here, it may be that because, yeah, if you take a look at how Z near and Z far are operating here for, we really need to find out one of these that's got all the values in it. I feel like that's a good... I just want a good drawing of it. Was this one had a good one, right? Did this have a good one? No. Does nobody just have just the actual? Because the thing is, in the book, in the OpenGL book, it's just got the drawing. And you can actually see what they wanted the perspective stuff set to. But it seems like everybody does not actually reproduce that diagram in a way that's easy to read, which is unfortunate. What's this? No. Do you have, do you have it drawn out? That is an actual matrix form. There it is. Okay. This is the same matrix that we were trying to look at before, but they've copied out the diagram properly with the actual ones in place. So see, there you go. That was what I was suspecting, right? So they put the focal length, which in their case is a field of view computation, but it's the same idea. They put that in the numerator because this will multiply into the x and y coordinates before divide. We were putting it into the denominator by putting 1 over it over here. I don't know if that will create a problem for OpenGL. I'm not sure. It's worth noting. But here's the part that's actually more relevant in terms of far and near clip planes, which we have to get right as well. Now, I knocked out the z value entirely, which means that I don't think we're having a problem with clipping. I don't suspect that that's actually the problem here. But I just want to go through, because I knew we had to do this, I just want to go through and get that correct as we go. So there's two things that could be causing us possible problems here, although I don't think the clip plane part of it's a problem, although this part could have been a problem. And that is just simply the part, the aspect of this, which is computing the near and far clip plane values. It's not really doing that. It's putting z into the correct range for near and far clip planes. But then also the part where, maybe it's required that we not put that in the denominator. Maybe it's required that we put it in the numerator. Because remember, OpenGL is going to do something. When we go through this transform, OpenGL is going to do clipping before it does the divide. So even though the way we were building the matrix will produce the same result whether we put it in the numerator or the denominator, it'll only produce the same result after the divide. So if it needs those values to be in a particular range beforehand, and we've done the computation in an order that still results in the same divide, that may not be sufficient. So again, just want to bring up the fact that we have to play by their rules entirely and put it into the spaces that they want. We can't just make something that we know will produce the correct XY values at the end or something. It's not that simple. All right. So that's easy enough for us to do, so maybe we should just do that. We've got 1 over focal length here. Really all we have to do is put the focal length up here. And so you can kind of see the way that's happening, right? We've got our terms. All we would have to do is we would just multiply by that. And instead of 1 over focal length, we'd just pass in focal length, right? That's all that we would actually have to do to make that substantive change. I don't think that's a particularly interesting change necessarily, but that's okay. What is a bit weird to me is that this is passed in as a -1, right? So the fact that that's passed in as a -1 suggests that the z values are going in the opposite direction, right? I'm interested to know if that's actually the case. Let's see. This is all doing exactly what we did. I'm just wondering why it's a -z. So a -z flips the z direction around. And I wonder if that's just because that's what they wanted to have happen, or whether there's some reason why we would need the z to run negative. Like, does OpenGL's screen space for some reason have z going the wrong direction? Well, you know what? No, now that I think about it, I guess that is true. Because when it's going to do the divide, it doesn't do a negation after the fact of the z. So even though it defines z, even though OpenGL normally uses a right-handed coordinate system, it's not going to negate the z that we pass in. So we would have to negate the z ourselves to make sure that when we do the divide, it does get negated. I say. All right, let's take a look at this. First of all, I'm going to go ahead and make it so that you don't have to pass in 1 over the focal length. So I'm going to go take a look at the perspective projection call. And I'm going to go ahead and just pass the focal length down, like so. That should be it. Okay. I guess I don't know why I'm running that, because we won't see, I won't be able to verify that the change is right, since we were not at a workable state to begin with, but that's okay. So yeah, if I want to put the focal length in here, that's all good. And then down here, again, I got to figure out that math. I don't like the idea that I'm not sure about the negation. More specifically, I'm not sure why the negation worked the first time. I guess the reason the negation worked the first time is because we were doing the subtraction ourselves. And in fact, I guess this may be the entire problem we were having. Because here's the thing. I forgot the fact that we implicitly, up when we were doing get render entity basis p, we were implicitly negating the z coordinate ourselves, right? This stuff's all gone now, like height off floor and all this sort of stuff. This stuff's all gone. That's a 0. Distance above target is also 0. So all that stuff is gone and doesn't do anything, right? And we now are putting the camera transform, which we used to be doing inside render entity basis p. We're now doing that in our perspective projection. What that means is we are no longer subtracting the z away, and so therefore we would have to flip the order in which it goes. So I guess I just never thought about the fact that we had already baked that in when we were doing it here, but we did, right? And just to like sort of go into that in a little more detail so it's clearer, let me go ahead and talk about that real quick. There we go. All right, so let's talk about that real quick, because I think I see now what I accidentally did when I was modifying these. So in my mind, right, the way that we had our coordinate system set up is we have an xy plane. Oops, that's the y. And z is coming up, right? That means that z gets higher as it gets closer to the camera. To get closer to the camera, we want a smaller value. But that's not going to be true as z gets higher. Now, because we were previously writing our own code for the projection, that wasn't a problem. Because all we did was we actually took and we did the subtraction this way. We said, hey, let's take whatever the point is, right? And let's subtract the location of the camera. That gave us a thing that was negative down z, right? And was getting, oh, not negative down z, that was getting higher as you went down negative z. And that's what I was stuffing into the z-coordinate. So obviously, when we built our projection matrix to match that, we could just put the z-coordinate directly into W and it would work. But now, when we're passing down just raw, now that we're having OpenGL do the whole transform, we're just passing down these raw coordinates. What that means is we need some way of flipping the z around so that as the z gets higher, things get further away. We need that to happen or our entire transform isn't going to work, right? Things would be getting bigger as they got further away and smaller as they got closer, which makes no sense at all, right? So you can see why we would need to do this here. I'm going to ignore, again, the z temporarily, but you can see why we would need to flip the z around at that point, because in order to do that divide, we need to flip the z value so that it will change the way its character, so that it will get bigger as things get further away instead of getting closer. When we do that, obviously, the z value, when it comes through and does that divide here, will then always be positive, because it will get clipped, presumably, if it was going to be negative, because it will be shifted forward by OpenGL, I would assume. But we'll have to double check that as well. Again, this is all about making sure that we understand what OpenGL is doing, because we're supposed to be preparing coordinates for OpenGL. So there we go. So that was actually the problem there, is that when I clipped out all that code, I forgot the fact that we had actually been negating our z. And now that OpenGL is getting this raw, it has to negate its z. OK. We still do have to handle the near and far clip plane, mind you. But that's a separate issue. So that's all well and good. And that's, that's fine. And that's good because that means we're now at the place where we are actually able to start doing some more stuff here, because now we are actually passing down z coordinates for everything, right? And that's good. You can see there, there's our screen rectangle too. You can see the unprojection is not implemented yet, right? You can see that very clearly, because that's the rectangle that should line up with the screen, and instead it's just this little tiny meaningless rectangle. So you can see we've got to get that fixed as well. But we're starting to get a little closer to reasonable here, right? So again, getting better. Excuse me, slowly. Putting the focal length out here into the numerator, again, that probably had nothing to do with it. We probably could still leave it in the denominator if we wanted to, I assume. Let's just check to see if that's true. I don't actually know if it is or not. Because again, like I said, we have to play by OpenGL's rules, not our rules here. So I'm going to put the focal length into the denominator here just to see what happens if I do. Yeah, so that was not the problem. We are allowed to do that, I suppose. That doesn't mean we should. It may still be that it's better behaved if you do it the way that OpenGL expects. But again, so it was just the fact that I had forgotten we were implicitly flipping the z's. We stopped flipping the z's and started passing them directly. And we had to account for that when we made our projection. We had to account for flipping those z's. All right. So let's try to finish up today. We still got some time left. We've got about half an hour left. Let's still finish what we were going to do today before getting into the near and far clip plane, because like I said, I kind of wanted to push those off until we were ready to actually do z buffering, because the near and far clip plane is really it's sort of intimately related, if you will, to doing that sort of z buffering where you care about what the z ranges are. And so I would like to talk about those together and rather than doing them now. So I'm glad that that was not something that we had to deal with. All right, so let's put that off for temporarily, and we'll deal with that next week when we start doing z buffering. And right now, let's just finish the camera part, which is the only other thing that I really had wanted to do. Inside the world mode, where we're actually setting the camera, you can see that we're passing some axes down here. All I really want to do right now is just kind of, I want to make it so that we can do some arbitrary rotation stuff. So what I'm going to do to start out with is I'm just going to make like a camera P. I'm gonna call this camera placement and this camera so maybe camera forward and camera inverse in some sense, because this is like the, or maybe camera object and camera or something like that, because this is the object. I want to create the object transform for the camera, like where the camera is in the world, basically. And then this is really the inversion of that, right? It's the thing that takes things and maps it into the camera space. So I just want to kind of call those two different things. So I'm just going to say that we've got a rotate. I think it's like, let's say around the x-axis, x rotation. I'm going to get an x rotation. I want to tilt the camera this way. And so if we're rotating about the x-axis, tilting the camera, if you imagine the right hand rule, remember I said things, align your right, take your right hand, align your thumb along the axis, and rotation, is going to go counterclockwise around there, right? You know this intuitively from the unit circle. When we draw, right, here's our standard XY plane, right? Z is coming out towards us, right? So if you imagine putting your hand there with your thumb pointing along the Z-axis and you curl your fingers, right? It goes in the same direction as the unit circle goes. The unit circle goes counterclockwise when we conceptualize it, right? So all of our rotations that we built, they go counterclockwise around the axle of the rotation if the axle's pointing out at us, right? So if I want to pitch the camera so that we're looking down on the world, it's pitched back a little bit, right? Well, that's actually the opposite. If I'm rotating around the x-axis, right, I'm going to rotate the world sort of toward me this way with a positive. So I want to do a little bit of a negative rotation along that axis. So I'm going to take, I think we have a value for pi here somewhere. There it is. So I'm going to take a value for pi here, and I'm just going to say, hey, pi would be 180 degrees. I want to rotate this very small fraction of that, maybe, a third of pi, maybe probably even less than that, a tenth of pi maybe. I don't know how much we want to do, but very, very little of a rotation, right? Pi being 180 degrees, right? Tau is 360 degrees. I want to do a very small fraction of that. So if I take that, what I should be able to do is just get column now and pull those out of the matrix where I have camera O. So, so now I can build any kind of rotation I want. And then my set camera transform should make that work. And again, that uses that world space offset of the camera. And what we're not really doing yet is I'm not placing the camera rotated around yet. So this is literally putting a tilt in, and the tilt's not going to quite be correct because of that. But that's OK. We'll deal with that in a moment. There we go. So yeah, so now our world is tilted. That's not the tilt I was expecting, though. Why did I get that tilt? So the rotation... Oh, duh. Because this is the rotation of the camera itself. So I was thinking about how I wanted to rotate the world, which is completely wrong. So let me think about that one more time. So here is my y. Here's my x. The world is laid out on it. Right? Here's my z. My camera is here. So what I want to do is I want to tilt the camera so that I'm looking this way, is what I was trying to do. Right? I was thinking about tilting the world, but that's not what I'm doing, right? We are trying to make it so that our camera is actually like a physical object we can think about. So I wrote all that code to assume that we were doing, we were going to take the camera as an object that we want to view things from. So yeah, so that rotation is going positive around x. So that's OK. I was like, got nervous there. I never like to negate things. Like, if I have something negated and I expect it to do something, if it does the opposite, that's like an alarm. That's like a huge, like, bad situation for me. I'm like, wait, what? If I expected this and I got the opposite, I assume I've got a problem in my pipeline somewhere. And I want to be absolutely sure that I know what the reason is for that before I switch it. I know that's a subtle thing, but it's like, yeah, if you're wondering why I didn't just immediately take the negative off and assume, I was like, I want to know that I just was thinking about some little thing wrong and that it really should be positive, not negative. Because the other possibility is that there's a problem somewhere in the math that we did before, and I don't want that to be wrong and be sitting there incorrect the entire time, right? That would be bad. Because it could create other problems later that are not so fixable as just removing a negative, right? So that's okay. So the other problem we have here is, in addition to doing that rotation of the camera, which we just did, right? So there you go. In addition to doing that rotation of the camera, which we just did, I also, that is pitching the camera up without adjusting where the camera's looking, right? So all we did was take the camera's location and look up from there, right? That's all we did. We did not try to move the camera in any other particular way, if that makes sense. Yeah. So this is assuming that the camera offset is in the world at that location and that it's looking this way. What I believe that means, and again, I just want to take some time to double check some of this here. It should mean that by the time we rotate to 90 degrees, we are looking straight away from, like, we're looking totally away from the world, and that is correct. Like, there it is. There's quite a bit of eccentricity here. I'm not sure if that means our focal length needs to be set differently. But hold on a second. Let's take a look at that. So that's what we wanted. This is exactly what we wanted here. And I want to be able to, in addition to that X rotation, I want to be able to rotate about the Z-axis as well, so that we can orbit the world, if that makes sense. So we're looking down on it, and I want to be able to orbit around as well. So in addition, I would like to be able to do some of this sort of thing. Right. And I'm not loving how I'm not loving what that focal length is. It looks like the focal length is maybe a little too eccentric. It kind of makes me feel like that focal length should be more. I don't really know. I'm just curious to see. That looks a little more sane to me in terms of the degree of stretch, right? But we can cross that bridge later. Take a look at that. So anyway, the other thing that I could do here is now we could actually have the mouse input correspond to that, but we'll get to that in a second. So what I was saying about that is, when we're doing this orbiting and stuff like that, the problem here is that we don't actually have any way of looking back, making sure we're focused on the world's actual focal point. So when we look at this world camera offset bit, what I want to do is I want to rotate that around with the world as I rotate as well. So, if you imagine how this is, like I said, the camera is out here somewhere. What I want to do is not just pitch the camera up, but when I pitch the camera up and look in this direction, I want to counter rotate its position so that it is looking at the center point. It's still looking at the same center point, right? Does that make sense? So when I rotate the world this way, I want to counter rotate the position of the world in the other way, right? But those are actually the same way if you think about it. Like, if I'm rotating this up, that's the same, that's going to rotate a position down, right? If that makes sense, because the position is coming out the other end of the directional pointing, right? Not sure I'm explaining that right. So if this is our Z, right? And here's the x-axis coming out here. Remember, the camera's axis is pointing backwards along z, right? That's where it's actually pointing, if that makes sense. So if I'm rotating it this way, it's looking back this direction. If I'm rotating it this way, everything wants to rotate by that rotation because, it's going to make it point that way, which is actually pointing back this way. And its position also wanted to rotate that way. So I should be able to take this right here, the camera offset. I should be able to take that and multiply that in, right? If that makes sense. Or not. When I say I should be able to do that, and then I clearly can't. So I should be able to do that. I should be able to rotate it out. And I would assume I assume that should be correct. Because that is what we do want to do that, right? I didn't do anything weird there. We want to be able to rotate the camera's offset by the camera O. We just draw this one more time. And we can knock out one term of this for debugging purposes just so we can see. There we go. So here's our X rotation. We have our camera. It's pointing like this, right? That's the camera's axis. And the camera's position is somewhere out here along Z, right? So it's, I don't know what it was something like 8, I think. So it's 8 along Z. So now what happens when we do our camera rotation is we're going to rotate everything this way, right? So we're going to rotate the position down here. At least that's our hope. And similarly, we're going to rotate all of the axes down there as well. So that's what we hope to do. But unfortunately, we're just kind of getting a collapse here. Like you can see, we're still drawing something, but it's kind of flattened out in a weird way. I'm not sure exactly what that corresponds to. Because of our multiplication here. I want to pull this out because I would like to be able to inspect these separately. So I'm just going to make a synthetic term there. And the other thing that's interesting is this should just be basically canceling out the work that camera transform actually does itself. So there really shouldn't have been much mystery there. So I want to go in there and make sure that we don't have any bugs because it feels like we probably do. All right, so let's hop over to world mode. Assuming I can actually find 13th. There it is. Okay. So here is our camera O. Here is our camera OT. And that is this when the offset's still 0? Okay, so I got to come back through the second time. There we go. All right, so now let's take a look at what our camera offset actually is here. So we're rotating 90 degrees. Oh. Wow, I'm an idiot. We're rotating 90 degrees. We should be seeing the world flat. We can't rotate 90 degrees and point at the straight. Yeah, okay, wow. So no, we don't have a bug. We just forgot we had rotated all the way down to 90. Nice work, Casey. Imagining bugs where there are none. So yeah, so we should be able to now do sort of that X flattening rotation, which is what we want, and still be pointed at the world, which again is what we want. So that's all good. And now what we want to do is we want to be able to hook these up to the mouse so I can spin it around, because that's what I want, again, for debugging purposes. So those two parameters I want to be able to control, if that makes sense. And so let's just take a look at how we might do that. So inside update and render world, I'm going to need an accumulator somehow, right? I'm going to need to be able to specify this. So I'm going to just do, again, something pretty stupid. I'm just going to do like debug camera pitch and debug camera orbit here. And I'm going to grab those values and put them into this equation. So rather than us having some arbitrary value that we put here, I'm going to go ahead and make the Z rotation be debug camera orbit, and the X rotation debug camera pitch. And then when we have these mouse stuff coming in here, I don't remember very much about how we captured debug input. I don't remember if we had any debug keys available. If we don't, we're going to need some, because we're going to need some way of saying that I want to access the camera now, and I would like that to be quick. So I want to be able to just hit like a accelerator key and have that come in. So let's take a look. We can see here we've got game controller input, which is not what we care about. Mouse button. So there we go. We've got Shift, Alt, and Control, which should be good. So I'll just use the Alt key for this and say if, input Alt down and input mouse buttons. I don't know how I get an is down for the mouse button. Is down, because those are game button states, right? So I can just say is down mouse buttons left, let's say. So assuming that that's true, then I can just take my mouse delta here. Do we have a last mouse X? I don't think we do. I don't think we do, so I'll save that as well. So I'm just going to go ahead and say that we keep a last mouse P, I guess. And store that. So now I can get the delta, which is all I really wanted, right? So when we produce this, we then have a D mouse P, which is just whatever the last mouse P was, subtracted away. So it's like, where did we go? And then in here, I can say what I want to have happen with the accumulators. So my world mode, debug camera orbit, and my world mode, debug camera pitch. I want those to be proportional to the mouse input. I don't really know what the ratio should be, so I guess I want to have a rotation speed thing here. Those are going to be in pixels. So for every pixel, I don't know, what percentage of pi I really want to go. I'm going to have to tune that to something reasonable, whatever feels right for that motion. And, oops, I meant that. Okay. Game mode world mode, last mouse P, it's debug. I guess I'll call it last mouse P then. So in theory now we should be able to sort of do this, and you can see that we can now do this. But I have to tune that and also get the directionality right. I guess I don't, it depends on how I want to orbit the world here. I guess I want that. I probably want the Y inverted. I don't know, that's hard to say. It's always a preference issue. But I definitely want it slower. There we go. No, I think I like the Y the way it was. And again, that focal length feels a little weird to me, so I'm just going to play with that a little bit just to see what the difference is if we change that focal length a little bit. That feels a little better to me in terms of what's going on there. I'm going to take a look at some focal lengths just to see what happens there. So let's say we change it to 2. Do you see how much more eccentricity there is? Like there's so much more like sort of warping there, and I like it better with less, I think, is my opinion, right? I just like that looks more sane to me in terms of how much of the world is getting fit in there, right? All right, so that's really all I wanted out of that anyway. And the reason for that is, like, right next weekend, what we're going to do is we're going to come through, and you can see everything's rendering in a flat plane here. And that flat plane is not really how we want things, because in order to start z-buffering, we need these objects to actually be kind of floating up in the air a little bit, depending on the circumstances. But the other thing that we need is we need for them to be oriented to the camera properly, and we need them to have z-values set so that they will properly occlude each other and all sorts of other stuff like that. So in order to see what we have actually specified in those terms, I need to be able to like set a debug camera here that can rotate around. And so we probably will need to do what we did before with the debug offset, where we can zoom in and out, right? We want to do something like that with the debug camera where the game will be looking at the camera and thinking it's one thing, so that it's setting all of its sprites based on that. But then we will then go and use also a debug camera offset, which we can set separately, that does this sort of offsetting so we can look. That way all the sprites will still align themselves to the other camera where the game's supposed to be viewed from, and then we can use this debug, right? And in fact, since I have about 6 or 7 minutes yet, if that makes sense, I probably, at this point, will go and just add that notion of the debug camera part in, I think. Yeah. So what I want to do there is just say, like, okay, the debug camera inside the render group, whenever we're doing that setting, we need sort of a way of the user thinking the camera's one thing, but us thinking the camera's something else. And so what we want to do there is say, yeah, when we do this push, right, and we sort of do like last proj there, right, we also want to store like last. I'm trying to think of how we would say this. So we want, in addition to last projection, we also want sort of the notion that people can get the camera that they're actually using, last user proj and like last actual proj or something like that. If that makes sense. And then we can put in that sort of debug camera. I'm not sure how we want to do this, I'll be honest. Maybe I won't do this today. Maybe I'll do this once we actually have that in there. Because I feel like we need, yeah, I'm not going to do it yet. I think what I'll do instead is we'll just make it so that here we can also do a thing where it's like, this way we can have the ability to zoom in and out as well, which seems good. So that would not be in proportion to pi for any particular reason, obviously. And there's some stuff that we probably would want to do here as well. This is one of those differential equation situations. Won't quite work. We'll talk about this a little bit later. All right, so what I wanted to do here is, I guess I won't try to correct for the speed stuff, but what I want to do here is have a way to like bring the camera closer or further from where it's supposed to be. So you can see that we've got that debug camera offset value that we're using here, and what I want to do is I want to have a way of interacting with that basically to move it further or closer. So we want camera offset to be that value, but then we want the ability to take camera offset and add to it a debug value for dollying in and out. I'm going to move this up to the top because this is actually the value that I wanted to work with. So I'm going to actually also do something here, and I'll talk to you about what that is in a second. It's kind of like a poor man's differential equation here, and we can talk about that in a moment. So let's go ahead and go over to the place where this stuff was stored and add ourselves a debug camera dolly in place there. And let's get that in there. There we go. And I think that should be all we need. So I think now, yeah, I can zoom, right? I can rotate around, which is what I wanted. And, you know, we can zoom in and see stuff clearly. Yeah, that's all we really need there. So that's all good. And that's nice because we can zoom in and see what we want to see and all that other goodness. I suppose that's probably a little bit backwards as well because we want to get closer as the mouse goes up. All right, so in this case, I wanted to talk about this here just really quickly. Like I said, a poor man's differential equation. So suppose that I did this the same way I was doing rotation, right? So here's me doing it the same way I was doing rotation, where we've got just the zoom, you know, and I can zoom in here. And what you can see is, like, as I move the mouse in here, like, okay, it's tuned okay for that, right? But as I get further away, you can see that I'm moving the camera. I'm like, the same mouse amount is like hardly moving the camera at all. You know what I'm saying? The reason for that is fairly obvious. The further away I move from something, the less the same amount of movement will, the less effect the same amount of movement will have. You know this is true because, for example, if I am standing somewhere and I'm looking at something right in front of me, this monitor, for example, and I take one step backwards, it gets much smaller in my field of view. If I instead look out the window at a building like way in the distance off in Seattle somewhere, and I take a step backwards, its size doesn't change at all, right? But since I happen to know in the game where I'm looking, I know the focal point is a particular point. No, I shouldn't say the focal point. I know the location we're looking at, right? Where we're aiming the camera at. I'm rotating around that. I know how far away it is. What I usually like to do to make camera controls more usable is to make the amount that I move be proportional to how far away I am. So once I get further away, I just will move more so that the amount of zoom appears relatively constant to the user, even though we're moving the camera by drastically different amounts. So what I do is I just multiply by the distance away, and then when I run it, now you can see it's fairly uniform through the whole degree, right? And even when you get close in, it's not touchy, right? It's still the same nice amount. And if it's a little too much, you can always just tune it down. Like maybe this is a little better. But that tuning constant now is clean and works through the whole range. So you don't have to have it really sort of ugly. This used to really make me grumpy in 3D packages like Max and Maya. They didn't do that. And so you'd end up zooming in on something and you'd be here and you want to zoom in a little more. And rather than it being nice like this, it would just zoom to nothing. It'd be like go right inside the object because even just 1 pixel was this huge increment in Z, right? But as long as you always use the distance to the thing you're looking at to modify it, you get a really nice clean zoom, and that's the way I think you should do it. The reason I called it a poor man's differential equation is because if you think about what's happening here, we're taking a value, which is the distance away from the camera, and we're modifying it using itself, right? The equation for the change in the dolly uses the value for the dolly in that equation, right? Here it is. And so what happens is this is only instantaneously correct, and the fact that we're not sort of doing an actual differential equation there means that for 1 pixel of movement we get 1 result. For 2 pixels of movement we will get a different result than we would have gotten if we did 2 1-pixel movements of the mouse, right? Which is kind of incorrect. That's not probably what we want. So what we really should do here is work out the differential equation. We're not going to do that with 0 time left, and we probably don't need to do that for a little bit later anyway. But that is just a note to folks out there. This should be an equation in E that would produce the correct results no matter what mouse you did, but that's a separate. Okay, Ace Flame Seer posts a very good question. And even though he posts a very good question, he said he's prefaced it with "sorry for being a dummy." However, you are in no way being a dummy. This is a very good question. It says, in the camera transform in 3D games, as far as I've been watching tutorials, there's something called an up vector. What is the purpose of it, and do we have it in Handmade Hero? Since it's a 2D game, I guess it's different. Your explanations have been wonderful, and I would love it if you could explain it. And also, thanks for doing EU-friendly streams, Kappa. Since I read it in hex chat, it's funny. I always see Kappa written out instead of having the little face. Anyway, no, that's a great question, and the answer is we absolutely do now have it in Handmade Hero because we are using a fully 3D camera, even though our game is 2D, just because I decided I wanted the full 3D flexibility there. And so we absolutely do have a thing that is an up vector. We're just not using it prescriptively, and I'll explain exactly what that means. The reason that we didn't cover it when we were doing this modification pass is because we kind of already have an up vector defined implicitly, and I chose to use a rotational definition for where the camera is, and so we'll sort of go through the other side of that now, so you can get the perspective on what that means. Why would I care what an up vector is? What's the deal there, right? Okay, so when we need to define a camera in 3D. The answer to your question is, in some sense, that you already understand what an up vector is. We just didn't call it that, right? You've already seen it laced through all of the stuff we've been doing. We just never called it out. And so all we really need to do now is to call it out and show which part of this whole process it was, and then you won't have to wonder where that up vector is coming in, right? So remember, what we said was we've got a camera transform. And in fact, you know what? Let me try to do this in the same order I did it before. I think I did it like this. So remember this. We have sort of this space where everything is aligned to something, right? And maybe we've got, like I was saying, we have specifying a triangle or something, or maybe this is a camera or whatever else, right? but we have objects, and they have a native coordinate system that we're thinking about them being defined in. And then we have some idea of them being placed out in the world somewhere in some other way, right? Their origin is displaced. This is 0, 0, 0 here, but here is some position that they have, right? And so, this is how we might think of this, right? And we talked about the object transform as the thing that goes from some rest space where things are defined out into the world where we have placed it, or into any coordinate system we want, but we've described its placement in that coordinate system by a transform, right? And in our case, that's typically the world, but you could imagine having subspaces or intermediate spaces or whatever. You are in charge of how you define your own spaces. You just have to describe transforms in those spaces, right? And so in our case, we've got a world space, so we describe these x, y, and z axes in the world space. We describe this point relative to the origin of the world space, and there it is, right? And more specifically, I guess we don't really even use world space. We use sim space, right? That local simulation region where everything's centered around the simulation center is really our space. It's not world space per se, because world space would be the whole game. We actually don't use that coordinate system, right? Because we map everything into a simulation region and do the simulation there. But anyway, that's the object transform, places things into some space we care about. The camera transform is the opposite, takes things and puts them back into a camera space where we know that we are looking down the negative z-axis, right? So here's where everything is that we can see. Anything that's back behind here we can't see, right? There's a clip plane, a near clip plane somewhere, like maybe right here, a little bit slightly 0.2 negative down the z-axis or something. There's a clip plane there, we can't see anything. In front of it, there's a far clip plane way out in the distance we can't see past or something. So there's a little bit of that, but otherwise everything back behind that xy plane we can see, right? And that's our camera transform. So now the question becomes, what is the up vector? Well, the answer is that the up vector is this vector right here in the case of the camera transform, right? Why is that? Because when we construct the camera transform, what we do is we provide a world space placement matrix, basically, right, for the camera, and we're sort of inverting that to get the camera transform. So we have the camera's placement, which is where it is in the world. We have the camera's axes in the world, the z, oops, that should have been an x. The x, the y, and the z, right? And then we're making a transform that takes everything in the world, so all the stuff that was out here, and we're moving it so that it's all right here, right? We're kind of like transforming everything back in the camera space. And to do that, we need those axes. Those axes correspond to real things in the camera's conceptualization of the world. The z-axis is the depth axis, right? And it's the viewing direction. It's the direction we're viewing in, is the z-axis. So you could call this like the view direction if you wanted to, right? We have a right vector. That's the x-axis, right? Because that maps to this. That maps to right in screen space. So this is the right vector. And furthermore, we have a vector that maps to what is up in screen space. That is the y-axis. That is the up vector, right? For the camera. So conceptually speaking, we actually already sort of know what the up vector is. It is the y-axis of the camera, right? That camera object, its y-axis, is the up vector, right? And we use that up vector to create the inverse transform by stuffing the up vector into the second row of the camera transform, right? Into the y row, not the column, because that would be an object transform. The y row, that is where we stuff that up vector, and that dot product with that vector transforms things into the correct space so that now this vector is the actual cardinal y-axis, which is what we need for that projection, right? So this is the up vector. But that's not the complete story. The reason that's not the complete story is because you then would very naturally ask, well, why are people talking about that in 3D? What do they really mean by up vector? Why is that coming up? Pun intended, I suppose. And the answer is because of how you might construct a camera transform if you don't already have the camera object itself, right? And let me tell you what I mean by that. This picture of the world is very sensical, right? It's saying, I've got an object somewhere in the world, right? And I've got a camera somewhere in the world that's a set of axes that look like this, right? And I know that I'm viewing down the negative z-axis of this object, and I know it's got an origin. So if I have this already, I know I can make the camera transform that views the world, whatever these other objects in the world are, all the objects that are there, whatever they are, I don't care, right? I can view all of them with this camera transform, and I know what the up vector is already implicitly because it's all defined for me. I have all this stuff already ready, right? But where people start to talk about the up vector more explicitly, and where I'm sure you've been seeing it, is because what if I didn't have that? What if I just had a point in the world that I wanted to view from, and I didn't know anything else, right? I had no idea where the axes were, what the axes were, right? So imagine instead of this nice picture where everything is clean here, suppose I don't have any of these axes. All I have is P, right? That's all I've got. And I'm trying to view the world using that knowledge, right? How would I construct this camera transform? Well, I know I need a bunch of things, okay? I need to be able to produce 3 axes from nothing, right? So the question is, what is the something I can have that will allow me to produce those axes? The point where the camera is known. So oftentimes what people say is, well, okay, I need something to look at. So give me a target, right? And maybe I'll just write that as T. So give me a target point. Now I know the vector to the target point, right? What does that give me? Well, that gives me my z-axis, right? Because I know the z-axis is what I'm looking down. So all I need to do to find my z-axis in this construction is say the z-axis, right, is just going to be the direction I was viewing in, right? I want it to go backwards, because again, I'm looking down the negative z. So I really want p minus t, which gives me this vector here, right? And that's almost the z-axis, but it's not unit length, right? I want it to be unit length. So I need p minus t, and I just need to divide by the length of p minus t, right? So it's normalized. That's the z-axis. Good, right? That's good. Off to a good start. Problem is, where are my other 2 axes going to come from, right? Where are my other 2 axes going to come from? Once I have the z-axis, I do know the plane in which the other 2 axes must be, right? Because the other 2 axes have to fall into this plane, right? The dot product of those 2 other vectors with z must be 0, right? Because it is orthogonal, this camera matrix, right? Remember from back when, it's orthogonal. What does that mean, right? It means that when I draw these out, when I'm looking at these, there's right angles between every last one of them, right? Every last one of these guys is orthogonal to the other. Know what I'm saying? So that means that if I know the z-axis, I know the plane in which the x and y axis exist. But what I don't know is their spin. Okay? So I know they have to be in this plane, but they could look like that. You know, they could look like this. They could look like that, right? I know they're at right angles to each other, so once I knew one of them, I could find the other one. But if I don't know either of them, there's an angle that I don't know. I just don't know how they're spun. So I can make up an x and y axis, but it would be any random skew of that. And if I'm trying to define a camera, I don't want it to be all tilted, because think about what that angle is. What's that angle, right? I've got the z, I'm looking down the z, I got my x and y axis. What is that angle? It's roll, right? So if I don't pick the right roll for my camera, I'm going to be viewing the world in some totally random way. And of course, roll is an actual parameter we want to control. Sometimes you want to view the world rotated. So what that means is we need one extra piece of information to define what the x and y axes look like relative to the z-axis. And that is where the up vector comes in. There's more than one way you can define an up vector, but it's basically a way of specifying what those other two axes should be once we can find the z-axis, because we can always find the z-axis if we've got a target. The only time we can't find a z-axis if we find a target is if we're sitting right on top of the target. But hey, guess what? You can't look at something if you're infinitely close to it, right? If you're right on top of it. So that's usually okay, right? That degeneracy should never actually occur in any practical scenario because it means you're doing something you fundamentally can't do. So you could just if around that and just set the camera to some, known identity configuration or something. So what people often say when they say up vector is they could mean multiple things. One thing they might mean about an up vector is just some vector which says a sense of up, which can be used to generate the x and y axes. That's one thing they can mean by it. So it can be a sense of up vector, and I'll tell you what that means in a second. The other thing they might mean is just, no, I actually need the y-axis, right? So if they say we actually are specifying the y-axis as the up vector of the camera, all that's doing is saying, hey, all right, I'm going to tell you what that y vector is. So now that you know that, you can trivially produce the x-axis. How? You can produce it with the cross product. I don't remember if we've covered that on Handmade Hero. We could cover that. We'll cover that maybe later. I don't want to cover it right now because we're out of time. But with the cross product, what the cross product lets you do is produce a vector that's orthogonal to two other vectors, right? So basically, if I say the x-axis cross the y-axis equals the z-axis, right? This cross product here, what that does is it says if you take two vectors and cross them, you get the vector that comes out of their plane in the order of the cross via the right-hand rule. So if I read in this order, if I say x cross y, I am imagining rolling my fingers from x to y and seeing what direction the thumb comes out. That's the z-axis, right? So the cross product will find those for you, which means that if I know that x cross y equals z, I can also do the same thing if I specify a z and a y. I know that y cross z will equal x. Why? Because I roll my fingers from y to z. Thumb points out the x-axis. So y cross z equals x, right? So if you were to specify the up vector, and that is actually y, then I know y cross z equals x. I now have all my axes. I found the z with this equation. I found the x with this equation, and the y was specified, so I never needed to find it at all, right? So that's one way. Another way of doing it is adds an additional degeneracy, but it makes it a little easier to use. Remember, in this case, what that means is the user, whoever's using this camera code, has to track the up vector the entire time. So as they move the target around, if they are pitching down on the target, that y vector has to be pitched properly to match the pitch of the target. So it's placing extra work on them. So it doesn't really necessarily help give you the whole cloth version of just give me a point, give me a target, and that's all I want. Generate the camera out of it. So another way people use the term up vector is to talk about a sense of up vector. What a sense of up vector is just saying what direction is up in general. Like in the general case, what do I mean when I say up, right? And so in our world, that's the z-axis, right? Our general sense of up is the world z-axis. It's 0, 0, 1. That's our sense of up vector. How does that help us in this case? Well, the reason that it helps us in this case is because our sense of up vector gives us another vector we can use to cross to produce the x-axis and then the y-axis, all right? How does that work? Again, I'm sorry we're a little short on time here, so this explanation is a little bit truncated. Hopefully it's helping. So what happens here when we take a look at how we're viewing things, right, is I have a point in the world and I'm viewing towards a target in the world, right? And my z-axis is coming out this way, which I know I can find. Question is, how do I find the other axes? Well, I know that the right vector must be pointing out here somewhere. The question is, how do I find what that right vector is? Well, if you imagine the world space looking like this, let's say, I guess that's not really our world, is it? That's more like our world, or maybe that's more like our world. So if you imagine the world looking like this, right, and I'm trying to look down on something here, And so I end up in a situation where, I'm looking down on something like this. So I'm up here, here's my camera position, here's the target, right? And I'm looking down on it. Well, I want to be able to find what my x-axis is here for the camera. And I don't know the y-axis. I don't really know anything, right? I don't know anything other than this one z-axis here that I can compute. Well, if I was to have an idea of what should be up, right? So we're basically saying there's a standard way that the user tends to want to view the world, and they want up to feel like up. So in general, I don't want to roll my view at all, right? I want to produce a view where up is up. And so no matter how I'm viewing things, I'm always still going to keep my orientation as upward as possible, right? So I'm never going to intentionally do this when I'm creating these views, right? Then what I can do is say, well, if I've got a general sense of up vector, which in this case is z, I can imagine taking the cross product of that up vector, right, with the z axis. That will give me my x for the camera, right? Why? Because those two are in a plane with each other. Remember, the tilt of the camera is just however high up I'm going to look down on something. If I take a vector that's pointed upwards and I have my vector that's tilted, when I cross those two, I'm going to get something that goes out to the right based on my view direction, right? With no roll. Because those are both in a plane, and I'm producing the vector that comes out of that plane, right? So what I do is I take my up vector, and I cross it with my z, and that gives me my x, right? Now, I have a z and an x direction. So I can just do the process one more time to get my y, right? Because I know, again, from looking at the diagram, that if I wanted to produce the y-axis, I could simply take z cross x. Remember, curl your hands from the z-axis to the x-axis, and the y should come out the thumb, right? I can just do z cross x, and that will give me my y. So that gives me the complete equation right? I compute z first, then I compute x using the up vector, and then I compute y given the z vector. I'm sorry, given the x vector I just solved. Now, the cross product is not normalized. It's actually proportional to the sine of the angle between the vectors. So technically, this is not actually the case. The x vector is actually up cross z over the length of up cross z, right? Just like this one. So these two have to be renormalized, if that makes sense. But that gives us the complete set of equations for generating the look-at. This is typically called a look-at matrix, or a look-at camera. That gives us the complete set of equations for a look-at. There they are, right? The z is p minus t over the length of p minus t. The x is up cross z over length of up cross z, so just normalize again. And then y is z cross x. And of course, those two are already normal vectors. So given that they're normal vectors, you don't have to renormalize them because they're orthogonal to each other and they're unit length. So the equation for the cross product happens to come out to length 1 anyway. But there you go. So sorry for the relatively compressed explanation. Again, I was just trying to finish up. Does that make sense to whoever asked? Ace Flame Seer? Okay, it sounds like that was good. All right, so I don't have time for any other questions. I'll just quickly scan to make sure that there are no other questions that are like super important questions that need to be answered right now. Would it be weird to change the focal length as the pitch changes, or should the focal length always stay constant? The focal length should always stay constant. If the focal length doesn't stay constant, you get this effect. This is what happens when you change the focal length. So if you want that effect, you can definitely change the focal length. It's called a dolly zoom in cinematography. But basically what it is when you change the focal length of the lens while the camera is moving, if you match the two, you get that sort of background compression change. But if you do it during pitch, it would make the world stretch out as you pitched. It would look like that. And if you want that effect, maybe you do, but it's probably going to be noticeable to the user. It's not going to be something they wouldn't notice, I don't think, unless it was a very small pitch change, perhaps. But maybe you want that. I don't know. All right, and then minor point. You called your variables pitch and orbit. Should probably be pitch and yaw. Well, I don't really like it to be yaw usually, because yaw makes me think of going like that, not like that. So that's why I typically call it orbit. I really want better terms for those. I want it to be like a word for orbital pitch and orbital yaw, which maybe the term should be orbital pitch and orbital yaw. I don't know, but that's why I never really like the names of those, if that makes sense. Anyway, all right, so let's go ahead and wrap it up. Thank you, everybody, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can experiment with it yourself. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot if you would like to know when we're going to be live, and an episode guide that you can use to catch up on past episodes. That's it for this week. I'll be back next weekend with more Handmade Hero. We will go ahead and start to try and use our Z-buffer that we worked so hard to enable in our 3D pipeline now. So we can start to have sorting without actually having to have sorting. So that's about it. Hope to see you back here for that. Until then, have fun programming, and I'll see you all on the internet. Take it easy, everyone.